Welcome to The Explainer. Today, we're going to pull back the curtain on something you do every single day to find out what really happens when you launch a program.
You know the drill, right? You click an icon and a program just appears. We do it constantly without a second thought. But what's the magic behind that click? What did your operating system just conjure up? Well, today we find out.
Okay, to really get what's happening, we have to start with a super important distinction, the difference between a program and a process. Now, they sound pretty similar, I know, but in the world of operating systems, they couldn't be more different.
So think of a program as a blueprint. It's just a file sitting there on your hard drive, a totally passive set of instructions. But the moment you double-click it, the operating system breathes life into that blueprint. It creates an active, living, breathing thing called a process.
A process is way more than just the program's code. It's a whole self-contained world. It gets its own private memory. You'll hear this called the heap and the stack, and a ton of other info the OS needs to keep tabs on it. And this is exactly why you can open, say, 5 different browser windows. Each one is its own separate process, doing its own thing.
Right, so your computer is juggling hundreds of these processes at once. You've got your browser, your music player, and a bunch of stuff humming along in the background. How in the world does the operating system keep track of all of this without completely losing its mind?
Well, it uses something you can think of as a little digital file card for every single process. The technical name for this is the Process Control Block, or PCB. This is the official record, the single source of truth holding every single detail the OS needs to manage that process.
And the very first thing the OS writes down in this little card is a way to give our new process a unique identity.
And that identity is the process ID, or PID for short. Yeah, it's just a number, but it is absolutely critical. It's how the OS, and even you, if you open up a task manager, can find and talk to this one specific process out of all the others running.
So, our little process now has a name, a number. Let's follow it on its journey. See, a process isn't just on or off. It's in this constant dance, shifting between different states of being as it fights for the computer's attention.
You can usually find a process in one of 3 main states. It can be runnable, which means it's ready to go, just waiting in line. It can be running, which means it's the star of the show, actually using the CPU. Or it could be sleeping, basically paused because it's waiting for something else to happen. So, right when our process is created, it doesn't just start firing on all cylinders. Nope, it gets put into the runnable queue alongside all the other processes that are also ready and waiting for their moment in the sun. And then, boom, it's time. The part of the OS called the scheduler points at our process and says, "You're up." Its state switches to running, and it finally gets to execute its instructions on the CPU. But what if the process needs something? Like, what if it's waiting for you to type something on your keyboard? It would be a colossal waste of power to let it sit there hogging the CPU while doing absolutely nothing. So the OS is smart. It puts the process to sleep.
The second you hit a key, the OS wakes the process up. But here's the interesting part. It doesn't go straight back to running. It has to get back in line. It goes back into the runnable queue waiting for its next turn. And this whole cycle, it happens thousands of times a second. It's wild.
This constant, ridiculously fast switching between processes, that's the secret sauce of multitasking. It's what creates the illusion that your computer is doing 100 things at once. But how does the OS pull off the swap so cleanly? The mechanism behind this entire magic trick is a core operation called a context switch. It's a simple, elegant 2-step. First, the OS saves a perfect snapshot of the process that's leaving the CPU, every last detail. Then it immediately loads the last saved snapshot of the process that's about to take its place. And that snapshot is the key to this whole thing. It gets stored in a special data structure called a trap frame. You can kind of think of it like a save state in a video game, perfectly preserving everything about the process while it's paused. The trap frame holds everything the OS needs to restart that process later, as if nothing ever happened. It knows the exact line of code it was on, that's the program counter, and exactly where it was in its memory, that's the stack pointer. It's a perfect freeze frame of that process's entire life at that exact moment. Okay, so to make sure all this juggling doesn't turn into total chaos, the OS has to be a really strict bouncer. It creates a super protected, isolated bubble for every single process to live inside. So every process lives in its own little virtual world, but this world is split in 2. You have the user space, which is where your app's code runs with limited permissions, and then you have the supervisor space, or kernel space. That's the OS's private club, where all the really critical stuff, like that trap frame, is kept under lock and key. This wall between them is so important that even the memory is separated. Your app uses a user stack for its own day-to-day business, but when it needs to ask the OS for a favor, like opening a file, it has to use a completely different kernel stack. And this separation gives us the single biggest benefit of all, security and isolation.
And here's why that is a massive deal. Because those two stacks are totally separate, if a bug in your application, or even a virus, messes up its own user stack, it cannot touch the OS kernel. This is the fundamental reason why one app crashing doesn't bring your entire computer down with it. It's a pillar of every stable modern operating system.
So, there you have it. A process is a dynamic, living entity, carefully managed and locked away in its own secure bubble. But that very isolation creates a really interesting new puzzle. If every single process is its own universe, totally cut off from all the others, how do they ever talk to each other?